Hello everyone. So in today's video, we're going to be looking at the scientific method, and this ranges from the types of data, your reliability, your validity, your accuracy, the key points in writing a scientific report, the key points in writing a scientific method, and yeah, just a general view, some errors that you might face in your investigation. So that's all we're going to be looking at. So just as an outline, we're going to be looking at scientific data, so all the measurements and stuff, that's what comes first over here. Then we're going to be looking at why there can be problems in experimentation and errors and mistakes and all that. Then we're going to look at how to write a scientific report, not a scientific paper, a scientific report. Then if you want to know how to write a scientific paper, look at my entire playlist on scientific papers, and I go through each component in very detail with examples, so you can check that out. Anyway, then we're going to look at graphing, the different types of graphs, line graphs, bar graphs, and when to use these types of graphs. Okay, how to make a line graph, what to add, what to not add, how to where and when what to use as your lines of best fit. So that's what we're going to be looking at. Variables, so independent, dependent, controlled variables, what are they? And then validity, reliability, and accuracy, and how that impacts the experiment. Finally, we're going to be looking at some scientific apparatus and then some circuit components. Okay, so let's just get straight into it. So let me just go straight to the top. Okay, the scientific method, scientific data. Data is the term given to all observations and measurements. So this is, data is what you see. So it's not the ball falls down because of gravity. That's not data. Data can be the ball falls down. So that's all the observations and measurements. And when you make observations, remember that you don't want to add any of your own knowledge. You're just writing down what you can see, hear, feel, taste, any of the five senses, right? So remember, data is always based on observations, and observations, you never give explanations. In observations, you don't give explanations. You just describe what is going on. Okay, so first of all, you have quantitative data. This is data that has a number or unit attached, number and unit attached. So this is something that you would use a number to describe. So the glass of water is 26 degrees Celsius. That's a number. Instead of saying the glass of water is at normal temperature, you're using a number. You can say the distance between me and the wall is 5 meters, rather than saying the distance between me and the wall is not very long, or something like that, right? So when you're giving numbers with a unit attached. Now, qualitative data, on the flip side, is data that is described with words. So here you use descriptions to describe what you see, what your five senses are able to make sense of. So I could say that my hands feel soft. Yeah, that's something that's qualitative. I'm not giving a number, I'm just saying it feels soft, or I say that it's really hot today. So in some cases, what happens is that you can give both qualitative and quantitative. So when it's temperature, you can say something is hot, but then you can also give them the degrees Celsius that it is. And so you're giving temperature as a qualitative and temperature as a quantitative. So you're using two. But in some cases, like describing how something feels, in most cases, you can only use qualitative data. And qualitative data is description. So it's really hot. It's really hot, the color of the car is blue, and so those kind of things. Okay, so that's like the first subcategory of data, so what the data is actually showing. The second is it first hand or second hand? So first hand data is data that you find by running your own experiment. So this is, you write an experiment, you do it, and then you get the results, and that's your data. Now, second hand data is data that comes from other people's work. So when you interview other people, or when you look at other scientific researches, when you read from your textbook, all of that is secondary. Now, experiment. Okay, so let's go into like the few key definitions. Experiment, a scientific test on a small part of the world around us. So an experiment, if you're running an experiment, you're not going to be running an experiment on the entire world. You're going to take a small part, it's going to be very specific, and you're going to have a very specific research-driven question, and that's something that you want to use. And so an experiment is just a small part of a small investigation of your entire thing. So let's say I can say, does the temperature of water impact the rate of cooling? That's your experiment, okay? And it's on a small part of the world, water and cooling. Now, what's an observation? An observation is what is seen, heard, smelt, felt, tasted. This is the information that scientists collect. So I think many people make this mistake that when they see observations, they try and feel as if they're the biggest scientists, and what they tend to do is that they give explanations for their observations in their observations. So let's say your observation is the ball fell down. All you have to write is that the ball fell down. Now, people think that they will sound smarter if they say the ball fell down because of gravity. But here's the thing: you can't see gravity making the ball fall down. So it's useless saying the ball fell down because of gravity, because now you're adding your own information. You do that much later. So right now, observations are merely what you can just see, nothing else. Okay? Now, you have two types of observations: qualitative observations that are descriptive. We've already looked at this. So for example, color, diet, habitat, temperature. And quantitative measurements, including numbers. They are of numerical value. So distance, mass, time, temperature, volume. Now, when it comes to quantitative measurements and observations, you need a unit, because in our first definition of quantitative, we looked at that it is data that has a number and unit attached. So here, what are those units? So if these are the following units used for measurements, as we can see here. Distances and lengths and heights are measured in millimeters, mm, centimeters, cm, meters, m, or kilometers, km. Small masses are measured in grams, g. Heavier masses are measured in kilograms, kg, or tons, t. Volume is measured in milliliters, ml, or liters, l. Now, the first 1, 2, 3 are all part of the metric system, okay? Now, time is measured in seconds, minutes, or hours. Temperature is measured in degrees Celsius. Now, the entire thing, the first three are part of the metric system. The entire thing is part of this thing called the System International Units, or the SI units, and these are a set of units to describe data that every scientist has universally agreed on. So let's say for distance, the SI unit is meters, right? So now no scientist can use miles. They can't say the distance between this and this was 72 miles. They're going to have to use meters if they want it to be published in a scientific paper, because that's what they've used. Meters is the dimension, is the unit that they have all agreed upon, and so this avoids confusion later when you write papers. And I think there was this one time where NASA crashed its rocket. I'm not sure if this happened, but I think people talk about this, that NASA crashed its rocket because NASA and Russia, they used different units of measurement. The USSR was using Russia was using this system, the metric system, and NASA was using its miles imperial system, and that's why they crashed the rocket. But I don't take my word for it. Do your own research on that if you're interested. Okay, so now you've got your observations. What is seen had smelt. This is the thing that you blindly write down. If the ball fell down, you write the ball fell down, because that's what you saw. You don't have to think about it. Just write what you can see. Now, inference is a logical explanation that aims to address the results and why it occurred. So the inference is where you give your explanation. The ball fell down, that's your observation, due to gravity. There you go, there's your inference. Now, so you're explaining why it occurred due to gravity. Now, or you can say something, or you can give a wrong inference and say the ball fell down because it was tired. Obviously, we knew that that's not true, but yeah, you have two types of inferences, the correct ones and the incorrect ones. And then you have a prediction. And a prediction is a projection of the data. It is based upon the observations made in the experiment and describes what might happen if the experiment was done in a different way. Okay, so what happened in the experiment? The ball fell down. What was your inference? The ball fell down because of gravity. What could your prediction be? Your prediction could be, if this mouse was thrown, it would also fall down. So your observation, let's run through this again. Your observation is what you write down, what you blindly see, feel, or all the five senses, and you write down. So the ball fell down. Your inference is a logical explanation. The ball fell down because it has mass and is attracted to the earth due to gravity. There you go, that's your inference. And your prediction is, this mouse will also fall down because it has mass and it is attracted to the earth because everything that has mass is attracted to a larger mass, and that's how gravity works. So in inference, you talk about how masses interact, and then you can say the ball and the mouse have the similar properties, and so you would expect this mouse, if it was dropped instead of the ball, to also fall down. Okay, and so you start off with observation, then you look at inference, then you look at prediction. Let's look at another example of this. So your observation is that cubes of sugar dissolves in tea faster when they're broken into smaller pieces. That's your observation. Smaller pieces, now here's your inference. Smaller pieces mix better with the water than larger lumps, making them dissolve faster. Okay, so now you go, that's that explanation. Now we apply that explanation to a different context. If the sugar is crushed even finer, then it will dissolve even faster. There you go, prediction. And so you can say something similar for like a salt, right? And so cubes of salt dissolve, crystals of salt dissolve in tea faster. Although you're not going to be doing that, you can apply this to salt as well. Since salt shares similar properties to sugar, it will also dissolve faster if it is broken up into smaller pieces. That's another prediction you get from the data. Okay, so let's look at problems in the experiment. Obviously, when you run an experiment, there's so many problems that happen, and so we're going to look at how these problems happen, what are they, and yeah, we'll just get straight into it. Okay, first of all, there are two types of problems: systematic errors, and these are consistent errors that will occur again if the investigation is repeated. This is like flawed methods or non-calibrated equipment. So what does this mean? Systematic errors, okay? So let's say you have a ruler that is very inaccurate. So at 1 centimeter, it measures when it's in real life 1 centimeter, your ruler measures 1.1 centimeters, and so it's consistently off and it doesn't give you the accurate measurements. In this case, that's a systematic error because you're using the wrong equipment. You get your measurements right. If something is you put your ruler on, you measure everything correctly, but it's not your fault, it's the ruler's fault. And every time you do this experiment with that ruler, you're going to get incorrect results. Your results are going to be, skewed. So that's a systematic error. There's no fault in the person conducting the experiment. However, this is an error, or it could be a fault, but remember, the main distinguishing factor is that this is an error that will consistently happen if it's not addressed, and it usually is that it happens unknowingly. So yeah, flawed methods. If the method is flawed, if the person doing the experiment read the method very incorrectly, or non-calibrated equipment, if the equipment isn't correct for its use. Let's say you're measuring the mass of this mouse and you put it on a measuring thing, the scale. You put it on a measuring scale, and the measuring scale is rigged. Now, even if this weighs 100 grams, your measuring scale will say 120 grams. Now, that's not your fault, the equipment is just not calibrated properly. So that's a systematic error. Next, random error. So a random error is something that will occur in an unpredictable manner and are generally smaller. They're usually one off and they don't happen much throughout the experiment. But this is something really random. So like the instrument doesn't function due to low battery. So your scale, although it works properly, it's on low battery. And so it doesn't function when you're measuring the mouse's mass for the first time. Okay, so this is random errors. It happens randomly. You can't say that okay, this is like it happened on it's gonna keep on happening, but it's just something that happens very randomly, and it's not going to happen again and again. If it would be a systematic error. So let's look at a more larger, broader list of problems in the experiment. Your first type of problem is a mistake. Mistakes are avoidable. They come from obvious tasks such as spilling chemicals or not using the correct material to conduct the experiment. So let's say you're conducting an experiment where you're supposed to dissolve 2 parts of water to 1 part of cordial, but you flip it around. You mix 2 parts of cordial to 1 part of water. That's a mistake. That's something that can be avoided if you paid attention. And so mistakes are avoidable. If you spill a chemical in your experiment, that's something that could have been avoided if you took the precautions or if you were more careful. And so that is a mistake. Errors, okay? Errors, on the other hand, unlike mistakes, are unavoidable. There are small variations in data collection that occur naturally, and sometimes they're bound to happen. So let's look at the 5 key types of data, of errors. So the first is parallax. Parallax is when our eye is never in line with the marking. So as you can see in this example, when you look at it at a right angle with the thing that you're measuring, this rod in this case, what you see is that we get a measuring of 6.2 centimeters. Now let's say you're looking at it at an angle from the top. So you're going down, and you look at the rod and you go even further down because, well, you're looking at it from an angle. And so when you look at something like this, this is the measurement you get. But when you look at something from this, you get a measurement much lower in comparison to what it actually is. So the person looking at from the top, if you can see what's going on, is that they're going lower than the actual measurement. So they're getting 6 centimeters. And similarly, on the contrary, on the flip side, the person at the bottom, they look towards the top, and so they get a higher measurement. So the person from the bottom, when they look up, they get 6.5 centimeters. Okay, so that's how that works. Now, so every time, to avoid parallax error, every time you measure something, measure with your eye. So measure it with the right angle to the thing that you're measuring. And whether this is, counting how much the volume or the length or the distance, make sure that your eye is on level with what you're measuring. Okay, limit of reading. Measurement falls between the two markings, which means that the value has to be estimated. Okay, so let's say I have a ruler and it is marked with every 1 millimeter intervals, right? And I'm measuring something, I've done everything properly, but here's the thing that I'm measuring is 0.5 millimeters long. Now, I'm at this point in my, I measure with my ruler, and what it shows me is that it's either between 0 millimeters or 1 millimeter. And so I have this limit of reading. I don't know what exactly it is. It can either be, in my case, since I can only see 0 millimeters and 1 millimeter, I can say it's either 0 millimeters or it's either 1 millimeter. So that's the problem I have, and I can't say it's 0.5 millimeters because I haven't got that equipment to measure it, and I don't know. And so limit of reading is when measurement falls between the two markings, which means that the value has to be estimated. If you look at rulers, which are again also marked at every 1 millimeter, they have a 0.001 centimeter limit, and this is a 0.01 millimeter limit because every 10 millimeters is a centimeter. So you're only accurate to your millimeter, and then anything after that, which is 0.1 millimeter, so every 0.1 millimeter, you don't know, you have to look at the 2 millimeters and then you have to make your guess. Next, instrument error. Some instruments only operate in certain conditions. Okay, so for this, let's take a look at metal rulers. Since metal rulers are subjected to expansion and contractions, they will expand and contract depending on the temperature, and as a result, if the distance between 1 centimeter is this much, when they expand in a hot temperature, it will become something like this, and when they contract in a cold temperature, it will be something like this. And so you have instrument error because your instrument is only working in certain conditions, and that impacts what you can measure, especially if you don't know that what those certain conditions are, and it kind of screws up your observations and your measurements. Okay, human reflex error. A stopwatch is accurate to 1/100th of a second, but our reaction is 0.110 seconds, meaning that we add extra time. When you start a stopwatch and when you stop a stopwatch, there's the human reaction time that you have to account for, and that messes up the data. So that's your human reflex error. Okay? And so a good way to combat this is to use video footage and do a frame-by-frame analysis where you don't really need your reaction time. Now, zero error. A mass measuring instrument doesn't measure zero when nothing is on it. Okay, this means that, let's say you have a scale and I want to measure the mass of this mouse. I put my scale, I turn it on, and there's nothing on it right now. It's supposed to measure zero, but it says something like 2 grams, or it says something like 200 grams, and so it's not measuring 0 when nothing is on it, and so therefore it's inaccurate. Okay, next, scientific report. So how do you write your scientific report? This is the next section. Okay, so when you start a scientific report, you want to start always with the heading, and this is the name and data of investigation and your partners. Then you jump to the aim. Describe what you are trying to do briefly. And this is something to remember, but every time you write about your aim, like aim, and then you have a semicolon, a colon, sorry, you always start with to test the impact of water on temperature or something like that. To, your first word should always be to, and then you can say to test, to assess, to evaluate, but the first word should always be to, followed by a verb. Okay, now that's a description of what you're trying to do briefly. Hypothesis. This is where you use your previous knowledge to form an educated guess about what will happen. So now that you've stated your aim, you want to tell them what's going to happen, and this is your hypothesis. So this is what you think will happen. This is how you respond to the aim based on what you know, what you've researched. And so, yeah, it's what you think. It's an educated guess. Materials or apparatus, which is a comprehensive list of everything used in the experiment. So retort stand, beakers, Bunsen burners, and yeah, so a list of everything that you've used. Those are some examples. Now, in the procedure, you take that comprehensive list that you made in your materials and apparatus and you put it all together. And it includes, and it's a description of how everything was done. It's a step-by-step description. So first, the beakers were filled with room temperature tap water or something like that. And you also, the best part to elevate your procedure and to make it look really good is to include diagrams and show how the apparatus is set. Because the thing is, you can make it as descriptive as you want, but there's always a limit to how descriptive scientific writing can be, because look, you're not writing an English narrative essay, you're writing a scientific report. And so you want to make sure that the procedure is really elaborate, and the person reading it can really understand what you're trying to do or what you're trying to say. And the best way to do this is with a diagram. So always consider putting in a diagram if you think it's really needed, and if you think it really helps your reader or the person marking your report. Okay, results. The results section is a complete list of your observations and measurements. And results, just think about it like this: results equals observations. When you talk about the result, don't add all your extra knowledge in there. Let's say your result is the ball fell down. That's it. Don't think about it. Just write the ball fell down. If you have a table, put the table in there. But don't write the ball fell down because of gravity. You just have to, you saw what you saw and you blindly wrote that down. And that's what you want to do. Now, your practical review, aka your inferences. Here, you give a description of what happened. You do a discussion of your results and what they show. Then you provide second-hand data to support your claim, and then you write about some problems you experienced. So your practical review is where you really put your inferences and your predictions about the data. Not necessarily predictions, much less, but do include predictions if you're talking about the application of your data. So let's say my results was the ball fell down. In my inferences, I say gravity is a force that attracts smaller mass objects to relatively higher mass objects, and so as a result, the ball, which is of smaller mass, fell down on Earth, which is of higher mass. Now let's say I want to give an inference on this, a prediction on this. So here's the thing, right? It would only be suitable to give a prediction if it was part of your aim. So now let's say I can make a prediction something like this shows that different planets go into another. This shows that these planets in the solar system revolve around the Earth due to the same concept of gravity, because different planets in the solar system move around the sun because they're attracted through gravity. And so that's a prediction that you made. And so your aim could be that why do planets revolve around each other? And your answer is gravity with this experiment. Obviously this experiment is trash to test the aim, but you get the point. Okay, conclusion, a brief summary of experiment, just sum up everything. Okay, graphing. Now, the thing with graphing is that you want to use the right graph for your data. So the first type of graph is a bar graph. That is one continuous and one numerical piece of data. Column graph, which is one continuous and one numerical piece of data as well. Histogram, stem and leaf plots are both two continuous, and your sector graph is proportional oriented, and your line graph is two continuous. Now you're probably thinking, what the hell is this guy talking about? Let me explain. When you have data, right, it's either categorical, which is qualitative, or numerical, quantitative. Now, when you have categorical data, it's split into two. Nominal, which means that it cannot be ordered, and ordinal, which means it can be ordered. So nominal, first of all, categorical is qualitative data. We've looked at this, colors, all that kind of stuff. Nominal is something that cannot be ordered. When you have a set of colors, red, blue, green, you can't order them because there's no basis. But when you have ordinal, you can put these things into order. So let's say unlikely, even, likely, certain. You can order that based because the probability. Obviously you're not giving a number, but it's able to be put in an order. So you have that over there. Now numerical is quantitative, and now you have two, continuous, which is part of a range, and discrete has to be an integer. So continuous is something like part of range, so height, distance. You can have 4.12 meters of height, or you can have 4 meters of height. It's part of a range. You get what I mean? And discrete has to be an integer. So the number of teddy bears you have. You can't have 5.11111111 teddy bears. You have to have 5, 6, 7, those integer numbers. Also, you can't have -1 teddy bears. That's a different thing. So let's look at a bar graph. When you have a bar graph, right, you have two axes, and so this one continuous plus one numerical is referring to the axes. Let's say the number of teddy bears. Let's say your bar graph shows the number of teddy bears that each person in your class has. Now, when I talk about continuous data, we're talking about something that is part of a range, and you have a bar graph. So on one side, on one axis, you have the names of people, so Amy, Bob, Charlie, let's say. And on the other axis, you have the number of teddy bears, right? So on one side, you have categorical data, because that is nominal data, that is qualitative and stuff that cannot be ordered. So Amy, Bob, Charlie. Now, you can't order that. You can say Charlie, Bob, Amy. Now, on the other side, you have continuous, discrete. You have discrete data. Sorry, you have continuous data. Sorry. So, yeah, so you have continuous data. So you can have 1 teddy bear, 2 teddy bears, 3 teddy bears, 4 teddy bears, 5 teddy bears, 6 teddy bears. So on one axis, you have all the teddy bears that you can have, and on the other axis, you have names. So one is dedicated to categorical, and the other is dedicated to numerical. So in a bar graph, you can have 1 continuous plus 1 numerical or categorical. So I do suggest that you think about this and use it depending on what you actually need it for. So yeah, so a simpler way to think about this is to think that for a bar graph, one axis has to be qualitative and the other axis has to be quantitative. Just think of it like that, and it makes more sense. Similarly, for a column graph, which is basically just a bar graph, you have to have 1 qualitative and 1 quantitative. And the thing with the reason why I said numerical is because, let's say your bar graph shows the rank of people, the rank that people achieved in your sports carnival, right? So you have first, second, third, fourth on one axis, and on the second axis you have the rank, how many people that actually achieved that rank. So when you have first, second, third, fourth, that is discrete data. That has to be part of an integer. Although those are numbers, those are discrete because they have to be part of an integer. On the other hand, you have continuous. So you can have 5 people that achieved first place, or you can have 10 people that achieved first place. And that's your axis, that's your quantitative. Both of them are quantitative, but this is your continuous axis and this is your discrete axis. Just think of it like that. I hope that makes sense. If you don't understand it, please leave a comment down and I'll try my best to explain it. Okay, histogram. You have two continuous. Stem and leaf plot, you have two continuous. So let's look at histograms, right? So for a histogram, as you can see here, is that you have the age. In this example, you have the age and you have the frequency of that people. Like, so you have, for example, 2 20-year-olds, 4 30-year-olds, 4 40-year-olds. And so in both cases, age can be part of a range, and so can the number of people you have. So both are continuous. Similarly with the stem and leaf plot, both are continuous. Now, sector graph is proportion oriented because you're splitting a pie. So a sector graph or pie chart is proportion oriented because you're splitting a pie into different pieces. A line graph is also two continuous, but obviously a line graph depends on the situation, but in most cases it's two continuous because on one axis you have an increasing number of, let's say, a value, and on another axis you have another increasing value, a range. Search up examples of a line graph and I think you will understand. Okay, observations. So now let's look at how you present raw data. This is how you present raw data. So you have a clear title, you have headings for each unit, and then headings for each column, and then you have units in brackets. Then you have a consistent use of significant figures, so, or decimal places. So let's see, this person has consistently used decimal places where they've written everything in two decimal places. So they haven't here written 38 and then here written 31.5. They've written 36.20, 31.20, 35.50. So you have to have that consistent consistent set of data and decimal places or significant figures depending on what you're doing. Now, samples. Samples are basically, in this case, trials. So this replicates the idea that they're grouped together. So the first row is grouped, the second row is grouped. Now, when you want to write your data, you have your independent variable on the leftmost side, and then you have your dependent variable on the rightmost side, and that's how you want to do it. Because this is testing the effect of current on voltage. So they're going to be changing current, and they're going to be measuring the impact on voltage. If you don't understand what independent and dependent variables are, we're going to look at that in a bit. Okay, this is where you bump it up when you want to represent your data to prove a point. And so here you want to always, when you make a graph, is that you always give a descriptive title to the graph or diagram. Now, you always mark axis values. You always write your values clearly, so, and it's at equal intervals. So you don't want to jump from 0 to 100 and then go 200, 300, 400. It has to be equal. 0, 100, 200. See, that's more equally spaced out. That's better. So always write your values clearly and use a similar scale for each axis. So if this increases 100 by 100 every 5 centimeters, make sure that is actually how it increases. However, the thing is, you can use different scales. So this can increase at a certain rate and this can increase at a different rate. But make sure that the rates are consistent within the axes. As you can see here, different scales may be used. Okay. Secondly, origin does not have to be 0, 0. Now give the quantity name in full units, so time, and then they've also had the units, so seconds and brackets. Then if you have an outlier, go back to your workings and check it again to see if you can explain why. So you also always want to try and explain your outliers, because the data proves what you're trying to test and your outliers disprove it. So it's also important to address your outliers. Finally, draw a line of best fit. Use a ruler for straight lines and a practice sweep for curves. Okay, lines of best fit. Let's look at the 6 key lines of best fit. First, direct or proportional relationship. Variables change at the same rate. Graph line is straight, slope is constant. Positive relationship, as x increases, y increases. Proportional, that's what you call proportional. Okay, inverse direct or linear proportional. So this is basically opposite, where when x increases, y decreases. So variables change at the same rate. Graph line is straight, slope is constant. Negative relationship. Okay. Now let's look at exponential relationships. As x increases, y increases slowly, then more rapidly. So as x increases, y increasingly increases. Now, inverse exponential relationship. As x increases, y decreases rapidly, then slowly until a minimum y value is reached. So these are like, the exponential relationship goes like this, and the inverse exponential relationship goes like this. Okay? Now, exponential rise, that's the next one. So this is when there's an exponential rise, then levels off or plateaus, so it stops rising, so it goes boom, and then it just sticks there. So and to describe this, as x increases, y increases rapidly at first, then slows, then finally does not increase at all. Y reaches a maximum value. And finally, when there's no relationship between x and y, as x increases, y remains the same. There we go. Okay, so we've looked at data: categorical, qualitative, numerical, quantitative, nominal, ordinal. For categorical, which is can be ordered. Numerical, you have continuous, where it's part of a range. Discrete, where it has to be an integer. Variables. Let's take a look at variables. So you have independent variable. This is the variable that you pick to change, and that is always the one that goes on your x-axis. So let's say I'm talking about the impact of temperature. How does temperature of water impact cooling? So what am I going to change? I'm asking, how does temperature of water impact cooling? So what I'm going to change is the temperature of water. That is my independent variable. That is the one that I picked to change. If I was to imagine a graph, on my x-axis I would have a temperature, I would have the temperature of water, and on my y-axis I'd have the rate of cooling. So first of all, your x-axis is what you change. In this case, it's the temperature of the water. Now the dependent variable is the thing that gets impacted. What are you testing for? In this case, I am testing for the impact on cooling. So my dependent variable would be cooling, and so my results would show a trend in how the water cools, and that's what I'm testing for. That is going to be my result. Now, controlled variables are what remains the same. So, how does temperature of water impact cooling? Where's the controlled variables? This is the things that you don't change, and if you do, it impacts the experiment negatively. So, let's say I'm talking about how does temperature of water impact cooling. The controlled variable would be the type of water, the electrolytes in it, everything, all of that, if the water is flavored or not. And so these things have the ability to mess up my investigation. And so I have to make sure that they remain the same throughout all my tries, throughout my entire experimentation procedure, so I don't mess up. And so those are my controls. I don't change them throughout the entire experiment. They're decided upon and then they're set aside, and then I'm just working with my independent and dependent variables. So remember, the dependent variable is always dependent on the independent variable. If that sounds confusing, forget it. Okay, validity, reliability, and accuracy. So, reliability, tested with repetition. And the thing is, there's a common misconception with reliability, is that you have lots of trials and they're very close together. Reliability only refers to the part where you have lots of trials. So if someone had 5 trials and someone else had 500 trials, the person with 500 trials would have more reliable data, even if the person with 500 trials as data was all messed apart and the person with 5 trials was all close together. Because here another thing comes into play, which is precision. How close are the measurements to each other? So, reliability is simply just testing more times, doing more trials. But precision is the actual assessment or the actual evaluation of how close are your trials. So, more precise would be something like how close would be when those 500 trials are closely chunked. And less precise would be when you have those 500 trials and they're very spread apart. But in both cases, you have 500 trials, so your data is reliable. Now, the thing is, in most cases, your teachers and everyone teaching you will equate precision with reliability. And if they do, just carry on with that. Now, that's how you define reliability in primary information. In secondary information, you're talking about how consistent is the information with other reputable sources. is the data presented based on repeatable processes? So is the data that they've given, can I test it myself and prove if it's true or not? Okay, accuracy. Have I designed my experiments to minimize uncertainties? Have I used repeat measurements to estimate random errors? Have I used the best measuring equipment available and used it correctly? So here is when you try and limit errors and not do mistakes and make sure that your data is very close to the true value that it's supposed to be. So let's say I want to calculate the mass of this. There's a true value that I can calculate for this mass. I can look at I can count the number of atoms. And so in accuracy, I want to make sure that my scale is not messed up. I've done enough trials with my scale to make sure that there are no errors or anything. Random errors, then no random errors. If there's a systematic error, that's the first thing that you should get rid of, a systematic error. Make sure there's no random errors. And have I used the best measuring equipment available and used it correctly? Now, in secondary information, is this information similar to information presented in peer-reviewed scientific journals? And is the data given with uncertainties, and are those uncertainties small compared with the measured results? So pretty much when it comes to secondary information are my results consistent with the calculated values? So if I use a measuring scale and I measure this to be 100 grams, and then I count the atoms, and then I do all the theory behind it of calculating this mouse's mass, do I still get 100 grams? So if my results are consistent with the calculated results, my data is accurate. Now, validity. Does my experiment actually test the hypothesis that I want it to? Have all the variables apart from those being tested been kept constant? So let's say you want to measure the mass of a HP mouse, but then in your experiment you measure the mass of a Lenovo mouse. Here you're not actually testing your hypothesis. Your experiment is not doing what it's supposed to. It's not testing its aim, and therefore as a result your results are not valid because they're not testing what they're supposed to. And so have all the variables been kept constant? No, because you've changed the type of mouse. Okay, so that's an example of something that's not valid. Now, do the findings for secondary information, do the findings relate to the hypothesis or problem? Are the findings accurate and the sources reliable? So first of all, when you're looking at other informations, do their findings actually relate to what you're talking about? And secondly, are the findings accurate and the sources reliable? So can you trust basically those sources? What you're seeing, is it close to the calculated value, and are those sources tested with repetition? And so that's something you want to look at. Let's look at the key definitions, and then we'll look at the examples. Reliability. All the results are tested multiple times. The results are consistent. Plus the results are consistent. So this is where precision comes in. Accuracy. The experiments have no uncertainties, no errors, and meet the calculated or expected standards. Validity, finally. Does the experiment test what it is supposed to? Does the experiment actually test for the hypothesis, or is it just there? So, in this case, let's look at this arrow and target case. And so, first of all, let's take a look at validity. Validity is how close is it possible to get the arrows close to the bullseye. And let's say you don't test for that. You test for how easy it is to not hit the bullseye. There you go. Your experiment isn't valid because you're not testing the hypothesis, the aim. And so that's reliability out of the way. Now let's say let's look at accuracy and validity. Accuracy and reliability. So accurate data is something that's close to the calculated values. Here your calculated value is your bullseye. So this data is accurate. Now, is it reliable? Yes, it's also reliable because the data is clustered. Now, secondly, this is accurate and unreliable. Here, you're close to your calculated values, but your data is not clustered, it's spread apart. Now, here, you have inaccurate and reliable data. The data, if it was accurate, would be at the bull's eye, but it's not. However, it is clustered at a different point, so it is over there, and it is clustered, so it is reliable, but it's not where it's supposed to be, so it's not accurate. Now, inaccurate and unreliable. The data is not where it's supposed to be, and it's not it's spread apart. It's not clustered anywhere. There you go. Scientific apparatus. This is something I can't really explain. Is this something you just have to just take a screenshot of and print it out and keep it with you. So, scientific apparatus: beaker, conical, flask, test tube, filter funnel, Bunsen burner, gauze mat, heat-proof mat, retort stand, test tube, rack, pulse head, measuring cylinder, clamp. Okay, filter funnel with filter paper. Let's take a close look at the pulse head and retort stand. So when you're usually making a diagram, you're not gonna just have a retort stand. You're gonna have to attach a clamp and a pulse head. So here's your retort stand. This is how you draw it, and then you have your pulse head, and your pulse head is the thing that connects the retort stand with the clamp. So it's a box like this. This is how it's drawn normally, and this is how it's drawn in the context. So your pulse head is connecting, and then you draw your clamp, and so here's your clamp. As you can see, there's an empty rectangle in the clamp, and in this case the empty rectangle is being filled with a filter funnel because it's a ring clamp, and so that's that over there. So now I'm just going to move my mouse and you guys can take a screenshot of that. Okay, done. Let's take a look at circuit components. This is wires when they're not connected, wires when they're connected. This is what a resistor looks like. This is what a variable resistor looks like, rheostat. That's what a lamp looks like with the X. There's another way of drawing it where you draw the ohm symbol, and I guess that one's more accurate than this because this can be any electrical component, but the one with the ohm symbol is specifically a lamp. Okay, but I think both are fine, but always check with your institution. This is a battery, this is a transformer, which is a variable power supply, which is a variable battery where you can change the voltage. This is a ammeter, measures the current. This is a voltmeter, measures the voltage. This is a open switch, no current is flowing through, and this is a closed switch, current is flowing through. There you go. This is the scientific method. I'll stream out so you can take a screenshot of both of them with my cursor to the side. There you go, take a screenshot and keep this close with you. So this is what the scientific method is all about. I hope you learned something, and I hope this video was able to provide some value to you. And yeah, and if you did, please tell me, give me some feedback, and I'll try my best to improve for the next one. Till then, keep grinding. Bye bye. Also, if you want to check out how to write a scientific paper, I've made a whole playlist on that from introduction to conclusion, and you can and it also has examples, so take a look at that. And then I've also made videos on electricity and chemistry, so that's where you can apply your knowledge on circuits and scientific apparatus when you now that we've learned it. So I hope this video added some value, and I'll see you in the next one. Till then, keep grinding. Bye bye.